Hello and welcome back to my YouTube channel or the Big Structure Hub. This is a place where you learn, build, and innovate. Before I can begin, I want to encourage those who have not subscribed to this channel to subscribe and hit the notification bell so that you may be the first person to be notified when I upload a video. In my previous session, I talked about design of singly reinforced beam, and under design of singly reinforced beam, I listed three items, that is design consideration. So the design consideration number one was bending, and number two was shear, and number three deflection. And at the end of that session, I promised you to tackle an example in my coming session, of which is today. So I won't be able to start solving examples. I want to finish first with theoretical part so that I may start tackling examples, practical examples. Now, today I want to talk about consideration number two, which is shear. So shear is discussed in clause 3.4.5 of BS 8110. So another way in which failure of a beam may arise is due to its shear capacity being exceeded. As the loading increases, an incline crack rapidly develops between the edge of the support and the load point, resulting of the beam splitting into two pieces. That is diagonal tension failure. So I want to go back to the previous session. In the previous session, you remember I talked about limit state design, and I said that we have two types of limit state design, that is ultimate state and serviceability. For the ultimate state is whereby you design a structure to prevent it from failing or collapsing. And for the serviceability, you design a structure for the comfort of the person using that structure or the person living in that structure. So shear is categorized under ultimate state. So shear can cause a structure to fail. So it can cause a structure to fail. For example, a beam. A beam is an element of a structure. So if a beam fails, then the entire structure can fail. So let's see how this shear can affect a beam or can affect a structure, the strength of a structure. So as you can see, this is a beam, this is a beam, and inside this beam we have the reinforcement. So these are the reinforcement, these are the main reinforcement, and these one are the shear reinforcement bars, and this is the support. From this statement, you have seen that as the loading increases, at an incline crack rapidly develop. So this is an incline crack, as you can see. So an incline crack rapidly develop between the edge of the support and the load point. So this is the load point and this is the edge of the support, resulting of the beam splitting into two pieces. So this beam can be splitted into two pieces as a result of shear failure. So this is diagonal tension failure prevented by shear reinforcement. So these are the shear reinforcement and this one are the main reinforcement. Then we have another figure here. We have another figure or another diagram. So Diagonal compressive failure occur under the action of large shear force acting near the support. So this is the support. This one will fail by crashing. This one will fail by crashing. So this type of failure, that one is diagonal tension failure, and the diagonal compression failure is avoided by limiting the maximum shear stress to 5 Newton per millimeter square, or 0.8 square root of FCU. FCU is the characteristic strength of concrete, whichever is the lesser. Then the design shear stress, which is capital V, at any cross section can be calculated from V is equal to V capital over BD, where V capital is the design shear force due to ultimate load, and the B is the breadth of section, and the D is the effective depth of section. So in order to determine whether shear reinforcement is required, it is necessary to calculate shear resistance, or use BS 8110 to determine VC, which is design concrete shear stress. VC is found to be composed of three major components. Number one, we have concrete in compression zone. Number two, aggregate interlocks across the crack zone. Number three, dowel action of the tension reinforcement. So design concrete shear stress, which is VC, is determined using table 3.11. The table assumes that cube strength of concrete is 25 Newton per millimeter square. So other cube strength up to 40 Newton per millimeter square is determined by multiplying the value in the table by a factor FCU over 25 raised power a third. So let me show you the table 3.11. So that is table 3.11, values of design concrete shear stress, which is VC, Newton per millimeter square, for FCU equals to 25 Newton per millimeter square concrete. It is table 3.8 of BS 8110. So that is the table. So if V and B, if V is less than VC, reinforcement is needed. So V is the design shear stress and VC is the design concrete stress. So normally done by providing, number one, vertical shear reinforcement. It is normally known as links. So these are the vertical shear reinforcement. Or number two, combination of vertical and inclined or bend up bars are shown below. So this is a combination. So this one is vertical and this one inclined. So the inclined is provided at an angle of 45 degrees. So vertical shear reinforcement is the most widely used method and will be one to be discussed. The discussion is as follows. Number one, shear resistance of link. Design shear force capital V must be less than sum of shear resistance of concrete, which is V concrete, plus shear resistance of link, which is V link. Otherwise, failure of the beam may arise. So V, capital V, must be less or equal to V in concrete plus V in link, whereby V in concrete is given by VCPD, and then V in link is given by D over SV ASV 0.87 FYV. So remember, we have capital V and a small v. So they mean different things. So V, capital V, which is the design shear force, must be less than. Now you take this and replace into this formula V concrete and V link. So VCBD plus, you take this one and replace it here. So it will be like that. And then dividing both sides by BD, you divide both sides by BD. So you will get V over BD is less or equal to VC. BD will cancel with BD you have divided with, plus 1 over BSV times ASV 0.87 FYV. We know that V, capital V over BD is small v, is shear stress, is shear stress. So we replace this one, the whole of V over BD with small v, which is shear stress, must be less or equal to VC plus 1 over this ASV 0.87 FYV. Then you rearrange. If you rearrange, you will get this formula. ASV over SV is equal to B into bracket V minus VC, close the bracket, divided by 0.87 FYV. So this is equation 3.15 in BS 8110. Then, where V minus VC is less than 0.4, the link should be provided according to this formula. Now you will replace V minus VC with 0.4. So you will have 0.4B over 0.87 FYV. So this is equation 3.16 in BS 8110. The two equations can help in calculating minimum area and the spacing of link, as I am going to discuss right now. So let's see how equation 3.15 and equation 3.16 can help us in calculating the minimum area and the spacing of link. So we proceed to number 2, which is form, area, and the spacing of link. So reinforcement should be provided in beams according to criteria given in table 3.12. So this is the table 3.12, form and area of link in beams. So table 3.7 of BS 8110. So here you have the value of V. So V is the shear stress, which is in Newton per millimeter square. So if V, which is the shear stress, is less than the design shear stress 0.5 design shear stress in concrete throughout the beam, then no link is needed, but normal practice to provide link in member of structural importance. So you will provide the links, but you will not design the link. So you just provide the link to hold back the main reinforcement. We go to this one. If V is greater than 0.5 VC but less than VC plus 0.4, you will provide nominal or minimum link for whole length of beam. So you will provide nominal or minimum link for the whole length of the beam. So this will be the equation. ASV is greater than 0.4 BSV over 0.87 FYV. We proceed to the last one, whereby V is greater than VC plus 0.4 but less than 0.8 square root of FCU or 5 Newton per millimeter square. Remember we said that we limit the shear stress to 5 Newton per millimeter square or 0.8 square root of FCU, whichever is the lesser. So you will design the link. Now you will design the link using this equation. So we want to break down this table whereby if V is greater than 0.5 VC but less than VC plus 0.4, we will provide nominal link based on equation 3.16. And if V is greater than VC plus 0.4, you will design link based on equation 3.15. Therefore, BS 8110 further recommends that the spacing of link in the direction of the span should not exceed 0.75 D. So that is all about shear. We now proceed to design consideration number 3, which is deflection. So deflection, this is in clause 3.4.6 BS 8110. The designer, which is you, must ensure that the deflection under working loads do not adversely affect either efficiency or appearance of the structure. BS 8110 describes the following criteria for ensuring the proper performance of rectangular beams. Number 1, final deflection should not exceed span over 250. And number 2, deflection after construction or finishes and the partition should not exceed span over 500 or 20 millimeter, whichever is the lesser. For span up to 10 millimeter, it is rather difficult to make accurate prediction of the deflection because of cracks and the degree of restraints at the support is uncertain. So BS 8110 uses an appropriate method based on permissible ratio of the span over effective depth. So the effective span of a beam, this is clause 3.4.1.2 BS 8110. So all calculations relating to beam design should be taken as the lesser of the, number 1, the distance between center of bearing. So this is the bearing and this is the center of the bearing. So this is distance A. So from here to here. Or number 2, the clear distance between support D. So this is the clear distance between support D plus the effective depth. So this is the effective depth. So for a continuous beam, the effective span should normally be taken as the distance of the centers of the support. So we have Roman 2, span over effective depth ratio. So generally, the deflection criteria in 1 and 2 above will be satisfied provided that span over effective depth ratio of the beam does not exceed the appropriate limiting value given in table 3.14. So criteria in 1 and 2, we already discussed that. So for number 1, you have the distance between the center of bearing, which is A, and number 2, the clear distance between support D plus effective depth D, like that. So this is the table 3.14, basic span over effective depth ratio of rectangular or flanked beam, which is table 3.9 of BS 8110. So you have support rectangular section, and then flanked beam with width of beam over width of length should be less than or equal to 0.3. So you have cantilever, which is 7, 5.6, simply supported 20, 16.0, continuous 26, and 20.8. You will see later how this one will be applied when I will be tackling more examples concerning design of beams to BS 8110. So the span over effective depth ratio given in the table apply to spans up to 10 meters long. Where span exceeds 10 meters, this ratio should be multiplied by 10 over span except for cantilever. The basic ratio can be further modified by factor taken from table 3.15 and 3.16 depending upon the amount of compression and tension reinforcement respectively. So deflection is usually critical in design of slab rather beams, and therefore modification will be discussed fully in the context of slab. So this is table 3.16. So that is table 3.16. So let me talk about the last item, which is member sizing. So span over effective depth ratio and maximum design concrete shear can be used for preliminary sizing members. So table 3.17 gives modified span over effective depth ratio for estimating the effective of concrete beam provided its span is known. The width of the beam can then be determined by limiting the maximum design concrete shear stress, which is VC, to say 1.2 Newton per millimeter square. So this is the table 3.17, span over effective depth ratio for initial design. So we have the support condition, span over effective depth for cantilever is 6, simply supported beam 12, then continuous 15. So that marks the end of theoretical part of singly beam design. So I will just apologize for not tackling an example, because I mentioned in my previous session I will be tackling example concerning design of singly beam, but I had to finish the theoretical part first, then we can start solving more technical examples. So for those who have not subscribed to my channel, I will still remind you to subscribe and hit the notification bell so that you may be the first person to be notified when I upload a video. So this theory is very important for the design of concrete to BS 8110, so don't take it for granted. Please, if you want the content to flow, you can navigate to my playlist so that you can watch how I uploaded this video from the first video up to the latest video. So in that playlist, you will just navigate to concrete design to BS 8110, and all the videos are there from the first video proceeding to the latest video. So I end there for today, and thank you for your time.